So in the last video, we looked at entropy, a measure of disorder. We said that nature favors an increase in entropy, an increase in disorder, which would make a reaction likely to be spontaneous. Now, in the past, we've also mentioned enthalpy, or energy changes, can affect whether a reaction is spontaneous or not. Exothermic reactions, which release energy, or enthalpy, are typically spontaneous. So this little equation here is going to combine both of those variables. And we're going to look at something called delta G. G stands for Gibbs free energy. Whenever I see Gibbs free energy, I always think of like the Bee Gees, like the Gibbs brothers. It's not the Bee Gees that came up with this equation, but it is a very useful equation. It's really going to let us take into consideration a couple different variables that could affect spontaneity. So one of them is delta H. Delta H is like that change in enthalpy, energy change. And we said that if delta H is negative delta H means the reaction is exothermic, that is likely to be spontaneous. Delta S was the change in entropy or disorder. We wanted that to be positive delta S. That meant there was an increase in disorder. And that also meant that the reaction was spontaneous. One other factor that could come into play here would be temperature. So if I think about this equation, delta H minus temperature times delta S, if I want to make sure that I can keep delta G negative, when you have a negative delta G, a release in free energy, the reaction is spontaneous under the conditions given. So if I look at this equation and I want to see, well, how do I keep delta G negative? We try to run this thing at high temperatures. So if I have delta H minus a large value here, by keeping the temperature high, I should make sure that my delta G stays negative, and the reaction will run spontaneously. A positive delta G means the reaction is not spontaneous under the conditions specified. Okay, so we want we want negative delta G, meaning that the reaction is spontaneous. So here's what they might give you. Something that looks like this. Oh, this is an easy equation. We're just melting an ice cube. Okay, so we've got water in the solid phase changing to water in the liquid phase. We want to calculate delta G for the following processes. Let's say we change the temperature. We run this at -10, 0, and +10 degrees Celsius. All we got to do is calculate delta G, and then we can look at the sign to see if it would be spontaneous or not under those conditions. They give me delta H, and they give me delta S. Well, that's convenient. So this is just plug and chug, right? Kinda. So these are all going to look really similar. We'll have our delta G equals delta H. This is endothermic. That makes sense. We can just use this straight up as 6.03 times 10 to the third joules per mole. And we only have 1 mole in our balanced equation, so that is just fine. This should be endothermic. Ooh, interesting. Endothermic typically means not spontaneous. Okay, so then we're going to go minus temperature times delta S. Well, look at our delta S value. This makes total sense. Delta S is positive. That would mean an increase in disorder. Well, nature favors an increase in disorder. I have two opposing forces. The reaction is endothermic, which is typically not spontaneous, but I do have an increase in disorder, which is typically spontaneous. I'm going to write that in there. This would typically be spontaneous. I guess it all comes down to the temperature then. So let's see what we got here. Temperature. Common mistake number 1. Look at these units. Kilojoules per mole and kilojoules per mole Kelvin. Often our temperature is given in Celsius. So you will need to switch them from Celsius to Kelvin. So let's do the first one. -10. So we'll plug this in then as 263 Kelvin. There's my temperature. So all I'm going to do here is take each of these bad boys and add 273 to switch them from Celsius to Kelvin. And then we can just plug this in. 22.1 joules per mole Kelvin. That's my delta S. So that equation up on top, it's really just plug and chug. I like that. And then we're going to do the same thing. The only thing different is we're going to change the temperature. So at 0 degrees, it would just be 273 Kelvin. And then at 10 degrees, we'd be at 283 Kelvin. All right, so let's plug this in and see what we get. Let's go -10 degrees Celsius. I plug this in, delta G equals, your units are going to be super easy. We have kilojoules per mole minus kilojoules times, or I should say, whoopsie, joules per mole minus Kelvin times joule per mole Kelvin. These guys are going to cancel. And you're going to have units of kilojoules per mole minus kilojoules per mole, or in this case, joules per mole minus joules per mole. Often they're kilojoules, but I'll deal with it. Okay, so I plug this in my calculator. 6.03 times 10 to the third minus 263 times 22.1. And I'd be looking at about 218 joules per mole. Hey, guess what? Delta G is positive. A positive delta G means this is not spontaneous. Well, duh! We're below the melting point. Yeah, at -10 degrees, an ice cube's not going to melt yet. That's not spontaneous at the temperature listed. You see where we're going with this, don't you? What if we're... let's skip. What if we're at +10? Okay, I'm expecting now that the ice cube's going to melt, right? Delta G. At +10, I have the 6.03 times 10 to the third minus, I'm going to skip to this guy, 283 times 22.1. Negative 224 joules per mole. And just like I expected, spontaneous. Well, yeah, because we're above the melting point. We should be melting. This thing should be going forward. Any temperatures above 0. Okay, so now let's do 0. I skipped this one, I guess kind of for a reason. At 0 degrees Celsius. Delta G. 6.03 times 10 to the third minus 273 times 22.1. And I would get about like -3.3 joules per mole. Okay, well, guess what? This kind of follows what I would expect. If delta G is negative, it's spontaneous. Anything above 0 degrees, we should be melting. Positive delta G, we are not spontaneous. Look at this guy here. It's negative. So will there be melting? Yes. There will be some melting occurring at 0 degrees. We're really close to equilibrium. When delta G equals 0, you're at equilibrium. Ah. So I guess we still get a little bit of equilibrium in our lives. We're really close to delta G being 0 at equilibrium. Well, guess what? When you are at the melting point, you are at a state of equilibrium. Oh. Where those two processes are kind of occurring at the same time. Again, this is slightly negative. So we are favoring the melting process. But remember how, like, at the melting point, you have both phases present? Like the inner particles are still solid while the outer particles are getting the energy. There's no temperature change. We are adding energy, but the energy used is breaking apart those intermolecular forces. Oh yeah, there is a state of equilibrium when you are at a phase change. Both phases are present. So yeah, this is slightly negative. So yeah, we are favoring the melting process. But you will have both phases present. Interesting. Well, there she is, delta G, Gibbs free energy. Gibbs free energy is great. It's a way of like looking at all factors that affect spontaneity. Temperature, delta H, is it endothermic, exothermic, and delta S, disorder. Are we increasing or decreasing in disorder? Let's try one more. All right, check out this little booger. Oh, it's another phase change. We're taking liquid bromine and moving it to gaseous bromine. For what temperature will the following process be spontaneous at 1 atmosphere? So like standard pressure. Okay, so let's see what we got here. For what temperature will the following process be spontaneous? So we want it to move forward. We want to be at the heat of vaporization. We want to be at the boiling point. Okay, so if we're at, that's an at, the boiling point, we should be in a state of equilibrium. We're at equilibrium. Between the two phases, both phases are present at the boiling point. Remember those curves that we kind of mentioned earlier? Well, I guess I shouldn't call it a curve. It's a phase change graph that kind of looks like that. So we're up in this area of the graph where there will be energy absorbed, but both phases are present. Okay, well think about this. When the system is at equilibrium, delta G should be 0. So we've got our equation, delta G equals delta H minus temperature times delta S. This is in the AP packet, by the way. If we are at equilibrium, delta G equals 0. Delta H minus temperature times delta S. Okay, well that helps a little bit. So let's see if we can kind of plug and chug. I eventually want to solve for temperature. And I guess I could rearrange this. I could add this to both sides, and I could say like temperature times delta S equals delta H. Or you could just plug and chug into this expression. I want to solve for T temperature. Let's see here. I do have delta H, and I do have delta S. However, this annoys me to no end. We have a slight issue, or I have an issue. Look at this. The units are different. I hate it when that happens. One of them is kilojoules per mole, which again, this would make sense. If you're trying to vaporize the liquid, delta H should be endothermic. This makes sense. A positive delta H, this is endothermic, which is typically not spontaneous, but it does have a positive delta S, which would be spontaneous, an increase in disorder. So it's all going to be temperature dependent. We got to flip one or the other. We have to make these the same unit. It really doesn't matter to me which one you want to use. So I don't know, like if I want to keep delta S as joules, I'd have to go 93.0 joules per mole Kelvin equals delta H. And then I need to make that something like 31,000 joules per mole. As long as they're the same, it doesn't matter which you switch them to, joules or kilojoules. And then we're solving this thing for temperature. So we'll take that 31,000 divided by 93. And I'd be looking at approximately like 333. And then you just have to be a little careful. This is going to come out in Kelvin because of this guy being in Kelvin. So if I wanted to, I could subtract 273, and I could say then that this would be equivalent to like 60 degrees Celsius. Either are acceptable. I mean, the problem might specify like at what temperature in Kelvin or in degrees Celsius. Or if it was manageable numbers and they gave you something like this multiple choice, obviously the choices would be one unit or the other. For what temperatures will the following process be spontaneous? Well, at 330 Kelvin, delta G is 0. So we would say at what temperatures? Any temperatures above 333 Kelvin, then this thing should be spontaneous. Because right now we're at 0. These two quantities are equivalent. So if I want a negative delta G, I need to increase the temperature so that I have delta H minus a larger value. Then I should keep a negative delta G. The second part of this then, what is the normal boiling point of liquid bromine? There it is, 60 degrees Celsius or 333 Kelvin. At that point, we're at equilibrium. We're at the boiling point. So if we want to make sure that we continue to favor the forward, we may choose to increase the temperature slightly. You are at equilibrium when delta G is 0. And when you're at a phase change, you are also at a state of equilibrium. I like that problem. That's interesting. Okay, so here's this last little thing that we should look at. This table from your textbook, it's beautiful. There's a multiple choice question that kind of keeps popping up that'll say like, under what conditions will the reaction always be spontaneous? Or under what conditions would we need a high temperature to make this reaction run spontaneous, or something like that. So here are our options. And let's think about this in terms of that equation. Delta G equals delta H minus temperature times delta S. Okay, let's do the two constants all the time. We want a negative delta G for this thing to be spontaneous. Okay, well, what variables then, what conditions would cause this to always be spontaneous? I'm going to move that over ever so slightly. Give myself a little more room. Negative delta G is spontaneous. Okay, well, what if we have a negative delta H? That means the reaction is exothermic. Exothermic is always spontaneous. And then what if we have a positive delta S? Positive delta S means an increase in disorder. And that is always spontaneous. These two conditions should always result in a negative delta G. If it's exothermic, we're going to have a negative delta H minus, and as long as this is positive, this is going to be negative minus some positive quantity over here. And it should always keep our delta G negative. So if we have these conditions given here, exothermic, negative delta H, and a positive delta S, increase in disorder, we are spontaneous at all temperatures. Even if the temperature was negative, then we'd be adding some quantity. We should always have a negative delta G. Check the other constant, that last one. When this is positive, if we have a positive delta G, it's not spontaneous. Okay, so let's look at the variables that would make this not spontaneous. Get rid of that in there. What if this was positive? If this was an endothermic reaction, that is not spontaneous. And what if this was a negative delta S? That means a decrease in disorder, which is not favorable in nature, not spontaneous. Then regardless of the temperature, you can't make delta G positive. You've got a positive minus, and if this is going to be negative, this is always going to be a positive minus a positive. This process is not spontaneous regardless of the temperature. So we're looking at this last option. It'll never be spontaneous if these two variables are both not spontaneous. So check out the two options in the middle. What if, again, you have opposing forces? Then it's all temperature dependent. It all comes down to this guy, delta T. So what if we had like this? It's endothermic, so you have a positive delta H. But what if you also have a positive delta S? So you want to make this delta G negative. What if you have a positive minus a really large quantity? A positive minus something really large could get me a negative delta G. So in that case, we're spontaneous only at high temperatures. Or on the flip side, what if this is exothermic, but we have a negative delta S? We want to keep this quantity negative. So if we have a negative minus a small value here, that should keep delta G negative. So in that case, we would only be spontaneous at low temperatures. So again, this is a very common multiple choice kind of question. And it all goes back to this equation, where they might say like delta H is positive, delta S is negative. At what temperatures will this be spontaneous? And they're looking for no temperatures, all temperatures, high temperatures, or low temperatures. Kind of like plug those variables into this equation and see what will it take to keep delta G negative. Then I know that my reaction will run spontaneous.